So before we do another couple of examples, I want to address one final question in this little workbook. What percentage of the variation in purchase totals is explained by a linear relationship to age? This sounds like a very complicated question, but what we'll see is after I kind of describe some things that are going on here, it ends up having a very simple answer. The answer ends up being the r squared value. So I want to take a second here and just give you a sense for how we can reinterpret the r squared value. So let's ignore the fact that we have a nice linear regression line for these. In fact, let's ignore the price of flour entirely. So we just have this group of cake prices, so a random sample of cake prices. We can kind of measure how much variation there is in the price of cake just by doing our own descriptive statistics. So one standard approach to this would be to compute a standard deviation. Or if you remember, the square of that is something called the variance. And something very close related is something called the total sum of squares. And this is another type of measurement for how much variation there is just in the price of cake. Now, if we remember that we do have, in fact, a nice predictive relationship here, a nice linear regression line, remember we talked about a measure of variation of between the line and the dots actually in our data set, right? Our sum of squared errors looked at the sum of the squares for these errors between a specific dot and the prediction made by the line. So this, in a sense, gives us a measure of how much variation in the data there is from the predictions made by the line, or the variation from the line, so to speak. So we're going to combine these two ideas. It turns out you can also compute r squared in a different way. R squared could also be computed as 1 minus the quotient of our sum of squared errors and our total sum of squares. And here's how we want to interpret this. The sum of squared errors is essentially the variation that we couldn't explain by using the linear regression line to define that relationship, right? The linear regression line makes the prediction, and then we were a little bit off. So the error that we add up by this sum of squared errors, this is the variation that we couldn't explain. If we ignore the linear relationship and even the price of flour entirely, we get a total measure of variation for just the price of cake. And so you can think of this SSE over TSS as essentially just quantifying what's the ratio of unexplained variation to the total variation for that price of cake. And this is going to be a percentage. It's going to fall between 0 and 1. And since we're doing 1 minus, this is kind of like the 1 minus trick. So if this is the amount of variation that's unexplained, and we're doing the 1 minus trick, we should get the complement, or the opposite. In other words, we can think of the r squared as giving us the percentage of variation in the y values that can be explained by the linear relationship to the x values. In other words, if this is the percentage of unexplained variation by the regression, r squared is going to be the percentage of explained variation. Here's another way to think about it, right? So we have a certain amount of variation in the blue dots, the up-down variation. So this is variation in the actual price of cake. Now part of this, because these dots are trying to follow the trend of this red line, part of this can be explained by the regression line. The fact that this dot is lower than this dot, part of that can be explained by the fact that the regression line is upward sloping. So what we're trying to do is break up the variation, the raw variation we see in our prices of cake, into the part that's just explained by the actual increase caused by the linear regression line, and the part that's unexplained by the regression line. And our r squared value gives us a percentage of that raw variation that can be explained by the fact that the dots are trying to follow this red line. Now keep in mind, the equation of the red line is a prediction based on the price of flour. So if r squared is the variation that's explained by the regression line, it's really the percentage of the raw variation in y that can be explained by changes or variation in the price of flour. So this is where we get our interpretation of r squared as representing the percentage of variation in the y values that can be explained by the linear relationship, right, the regression line, to the x values. So if we jump over to our example, what percentage of the variation of the purchase totals is explained by a linear relationship to age? Well, keep in mind our R squared value is sitting right there on the chart. So let's just highlight this. Our R squared is a 0.5637. So since R squared is 0.567 we can say the following. Oops, let me just bring this down. All right, we can say the following. 56.37% of the variation we see in purchase totals, all right, our y variables, can be explained by the linear relationship to age, our x variable. So we literally take this R squared value, which always falls between 0 and 1, and we interpret it as a percentage of the total variation in y that can be explained by the linear relationship to this input variable, or this independent variable x, age. We've covered a lot today. We talked about exactly how we define this line of best fit. How do we actually choose the line that goes through these points? And essentially we found that it's the line that minimizes the prediction error as measured by a statistic called the sum of squared errors. We've also talked about the typical ways that we use our regression line for either making predictions or to further quantify or describe the relationship between our two variables. Typically, this is done by interpreting the slope in a specific way. Lastly, we saw a nice reinterpretation of our R squared value as essentially determining the percentage of variance in the response in the y variable that can be explained by the linear relationship to x, or in other words, can be explained by the fact that the regression line should be causing either increases or decreases in those y values as our x values change. So what I want to do is do one more final example. We're going to jump back to our Excel workbook, and we're going to look at example 3, and we're going to walk through some practice questions with all of these things. All right, so we have a correlation coefficient of a negative 0.733. So in terms of just the magnitude, if we cover up the negative sign, this is relatively close to 1. So this is, kind of a medium strength correlation. We also know it's a negative correlation. So when we go to plot our scatter plot, which we'll do below, we should expect the dots to sort of loosely follow a line that's sloping downwards as we move to the right. To determine whether this is significant, remember we're going to need to use that workbook correlation / p-value that's located in either your week 12 or your week 13 materials. Before we can do that, however, we do need to know our sample size, which remember is just going to count the number of rows that we have. So I'm just going to select A3 out to A56. So I'm only counting how many, what's the number of rows that I have in this case by just counting one of my variables. So I have a sample size of 54, and let's call this correlation a negative 7.34. So if we jump over to our other workbook, we can type this in as a negative 0.734. Our sample size we said was 54, I believe. Yep. And we can set a significance level of 5%. I didn't mention a significance level in this case, but you can see that even though the p-value is so incredibly small, it doesn't really matter. Any reasonable choice of a significance level, we would end up rejecting that null hypothesis that at the population level, the correlation is 0. So in other words, we do have a significant correlation here. So we would say, yes, our correlation is significant. Correlation is significant because our p-value is well below, let's just say, the standard 5% significance level. So again, as a quick summary, therefore, there is a relationship at the population level, right? If we were to collect everybody's BMI and how many steps they take per day, at that population level, there's a relationship between BMI and steps taken per day. Okay? I'm just going to move this over here. Steps taken per day.